Good afternoon, friends, and so this will be a very short one because we need to complete the quiz after this and then be ready for the valedictory by 4 p.m. So, I will vastly curtail down on what I had originally planned to present yesterday and just give you a more or less a feel of what is porous media and what are the parameters to look for when we talk about condensation and boiling in porous media. Okay. And what I will do is there is a book chapter which was written in the 90s, and that is still probably the most comprehensive book chapter or any review paper that exists on boiling and condensation in metal in porous media. So, I will probably upload that chapter, a PDF version of that on that shared drive, okay, for you to download. So, let us get started, and I will first start with a few words about what is porous medium. Okay. A porous medium, as the name suggests, consists of a solid and a fluid phase. Okay. If you think of sand or mud or soil, this is all porous medium. Even when you talk about rocks, those are also porous. We know that petroleum or crude oil exists in the pores in rocks, right. That is where we extract it from. Okay. So, when we talk about transport in porous media, there are few terms that we need to talk about, particularly two terms that we should think about. So, let us write down that. What we spoke is porous media definitely has a solid plus fluid phases. Okay. Now, what we will do is we will talk about two important parameters of a porous medium. The first one is called porosity. So, porosity is the void fraction by volume or the fluid fraction by volume, right. So, when we talk about low porosity medium, it means that it is primarily solid, but has some voids or interstices in between. When we talk of high porosity medium, what we mean is most of it is fluid and very little is solid. Okay. The next one that also is very important is known as permeability and typically denoted by K. Okay. Keep in mind, porosity definitely is non-dimensional. Permeability, on the other hand, has dimensions, and it has dimensions of length squared. Okay. Now, what is permeability? Just briefly say where the origins are, and that is where we also pay our tribute to Henry Darcy, probably the forefather of transport phenomenon in porous medium. Darcy did a lot of work on porous media, but one of the most significant seminal work that he did was he did a series of experiments for flow of a liquid through a tube which is filled with sand to start with, and then he used other particles, etc., and he measured pressure drop. Okay. So, let us say this was his tube and this is filled with porous medium. He was having some fluid flowing in and flowing out, and he was measuring pressure drop at different velocities or flow rates. What he found was that when you measured pressure gradient in the flow direction, this is x, he found that it was proportional to, first of all, the velocity. It was also proportional to the fluid viscosity. Okay. And then he also found that as he made the bed more and more packed, the pressure drop became higher, and that is intuitively is correct, right, we know. So, that is where we found we have today the famous Darcy's law, which says that the pressure gradient is mu u over K, and this K is your permeability. Okay. and this is true for any direction. This was unidirectional flow. So, if I have to write it generically, I would write Darcy's law as delta p in the tensor form, del x I will be mu u I over k in the direction. Boiling and condensation, you have two phases of the same fluid, in the liquid phase and in the gaseous phase, but that is also multi-phase flow through porous medium. So, that is why what we are talking about today is actually a subset of multi-phase flow through porous medium, which is phase change or boiling and condensation. All right. So, that being said, let us move on to the first one, where we talk about condensation. I have to be very, very cognizant of the time and finish no later than 3:30. Okay. So, when we talk about condensation of porous medium, there can be variety of configurations. I am only going to talk about condensation on a vertical flat plate, which is what you have studied, I think, on Wednesday night or Wednesday afternoon. Okay, you studied this one, where you have vertical flat plate, and then which is at a temperature T wall less than the T saturation of the fluid which is surrounding it. And as a result, what happens is you have a condensate film that forms on the bed, or sorry, on the plate, right. And then of course, there is a, we also learn it in our regular fluid mechanics heat transfer class, that there is, this is film condensation, and you have film thickness which gradually increases with distance. Okay, I should mention that this is the direction of gravity, clear. And over here, now let us say this is what we have, this is what we have learned. Now, what I am saying is, well, this is a vertical plate, no doubt, but on the vertical plate I have a porous medium. So, this is not just thin air, this is actually a porous medium which is attached to the vertical plate. If that is the case, then what happens? Okay. So, this is where it becomes a little tricky. So, liquid will still flow down, right. So, liquid flows down, no doubt about that, because gravity is acting. So, liquid flow, number 1, along, let us say this is x, okay. We will name this as x and this as y. So, along x, due to gravity, but at the same time this is a little more complex. It is not going to be always vertically downward flow. Why? Because I have a porous medium, and so there will also be some flow along y due to what is the force? Capillary effect, due to capillarity. Or capillary effect. Okay. So, now if I consider, let me draw a picture over here again of the plate, and let us now consider a very simple porous medium in 2D. Let us consider it is an array of cylinders. Okay. Actually, let us consider it to be an array of cylinders, just for the sake of simplicity. It is like this. Okay. Then I have one more layer like this, maybe one more like this. I wish I had a different colored pen. No, they are all black. Okay. Then what happens? If the typical diameter or the length scale of the porous medium is d, I can have 3 scenarios, and then this is again my liquid film. So, I can have 3 scenarios. The first one is my film thickness is less than d, my film thickness is comparable to d, or my film thickness is greater than d. Okay. So, 3 scenarios. Okay. Now, the last one that you see here, delta L, which is greater than d, or I would say much greater than d, what that means is this is a case where we normally don't, what should I say, don't really look at what is happening at the pore level. Okay. We assume that what is happening, it is all encompassed or whatever within the film thickness except at the very leading edge over here. Other than that, most of the randomness of the porous medium is already incorporated inside the liquid film. Okay. On the other hand, if these are really big, then in that case we cannot do that. So, over here these are the two cases where we need to go down to direct simulations. Okay. At micro level, sorry, what did I do? Okay. So, here we have to look at micro levels, but however, when delta L is much greater than D, we use what is known as volume averaging approach. What it means is, I take the average properties of the porous medium and do my analysis based on that. Okay. It will be a little more clear when we talk about it. Okay. So, what I will do now is I will just show you didn't go. Okay. So, sorry, maybe the slide mode is doing something, I do not know what that is. Here it is. So, now if you look at the screen, these are the three scenarios I am talking about. The first one is when the liquid film is very small compared to the characteristic length of the porous medium, length scale of the porous medium. The second one is when they are comparable, the third one is when it is much larger. Clear? Now, as a result, what happens is, if we consider the last case, and which is the most generic case where we can apply what we call the volume averaging approach, what we see is in the first region very close to the wall, you have a layer of only the liquid. Okay. This is very characteristic of porous medium. Okay. Then next to that, if you look over there, then what you see is there is another layer which will have both liquid and vapor, and then outside that layer you will have just vapor. And again, keep in mind, entirely we are talking about porous media. This whole, all these, both these layers are inside the porous medium. Okay. So, as I move away from the wall, I will first see a layer which is only liquid, followed by a layer which is liquid plus vapor, and then only vapor. Okay. So, that is how it is. And so, therefore, now things become a little more complicated, because I have to analyze whatever the continuity momentum energy equations for both of these layers. Okay. So, this is where things become a little more complicated. Nevertheless, because of the lack of time, what I will do is I will not get into those details. I will briefly just mention and then move on. My God, it is already. I will also talk about, you already know this, bond number. Bond number, what is the ratio of the two forces physically? Huh? Body force by surface tension, or in this case what I wrote in the first one, buoyancy or gravity over capillary. Okay. So, we know this, you have seen this several times, rho L minus rho V divided by sigma, this part you know. Now, what comes in the bond number definition for a porous medium is slightly different now. In the most generic definition, here we write it as permeability over porosity. Okay. But again physically this is gravity over capillary. So, therefore, what happens is when bond number is much lesser than 1, capillary dominates. What does that mean? What that means is, if you look at that, if you remember the figure that we were seeing, the percolation of the liquid layer into the porous medium will happen earlier, okay, because gravity is weak, capillary is pulling it down. It wants to move down, but the capillarity is moving it outside. So, the liquid layer becomes thicker. On the other hand, if bond number is greater than 1, gravity dominates. So, which means, yeah, the capillary effect forces would like to pull it away, but then the gravity forces are so strong that it wants to go down. Yeah, I am going down. You can try as much as you want, but the response is not going to be great, right. So, these are the two cases. Okay. Now, what happens is, a side note, a case where gravity dominates, where bond number is much greater than 1 actually, the two phase region, the delta L plus delta V that we were seeing, that many a times is either very weak or absent. Oops. I don't know, every time I change it does not show. So, this layer is either very thin or it is absent. Why? Because most of the liquid, as soon as it forms, as soon as it is formed, would like to fall down. Very little will move out due to capillary action, right. So, when bond number is much greater than 1 and gravity is the dominant force, then you will probably end up with only a delta L and probably a negligible two phase film. Clear? All right. Now, let us do a thought exercise. Okay. If you look at okay. The generic case again, you have a delta L, you have a delta L plus delta V. Okay. Of course, you have liquid flowing down, here also it is flowing down. This is only L, this is liquid plus gas or vapor, right, sorry. Okay, liquid plus gas. By the way, keep in mind that in both of this there is also solid, which is the solid of the porous medium. So, I am not writing that. Okay. Now, tell me how these things will vary. First of all, let me write this down, and this is distance y, correct. Again, this is g for the sake of completion, this is x, this is y. If I want to see this is delta L, this is delta L plus delta V. If I want to look at the liquid fraction, what is it going to be here? Going to be 1, right, because it is completely liquid, and at this edge it is going to be 0. So, what happens is, typically if you look at the liquid fraction, it comes down like this. Okay. So, this one we call it S, which is liquid volume fraction, goes from 1 to 0. Clear? Now, tell me what happens to temperature. Of course, temperature over here is T sat, we know that, and at the wall is probably T wall, right. So, the temperature actually goes up like this, and many people say that in the two phase region, even though it is two phase, the temperature is more or less constant, because there is very little condensation, and that too with subcooling that happens on the walls of the solid phase. So, even though whatever is condensing on the solid phase, that is actually what is because what is going out from the surface over here due to capillary action, and that is more or less at the saturation temperature because it is in equilibrium with the gaseous phase. This is an approximation, by the way. Of course, there will be some difference, there will be a little bit of a gradient here, clear. So, this is temperature. Finally, if we were to want to plot velocity of the liquid, how will it go? Velocity definitely 0 over here, and it is 0 over here. So, typically the velocity actually goes down like this. This maximum value happens a little before the liquid film. Okay. It starts to decelerate before, and so this is your u max and this is your u at the interface, clear. Okay. Now, keep in mind, I will also write down one thing, u m is typically less than u max theoretical. Now, why do I say that? What is u max theoretical, you will ask? U max theoretical from Darcy's law can be shown to be this, k over mu L G rho L minus rho V. If you consider idealized one dimensional flow, this is the maximum velocity that it can attain for a given permeability, for a given gravitational force, and for a given viscosity, follows directly from Darcy's law. Okay. But actual u max will never be equal to that. In practice, it reaches, number one, it reaches the maximum value slightly before the interface with the, or slightly before the where the liquid film ends, and that value is less than this theoretical maximum. All right. So, this is what I am showing here as well. Exactly the three things that we showed, this is what it is. Okay. All right. The other thing I want to mention is, over here, if you are doing analysis, over here you will have to take only liquid, whereas over here you will take liquid plus vapor. So, sorry. Okay. So, just to give you an example, here you will have only del u L del x plus del V L del y equal to 0 for continuity, whereas here you will have del u L del x plus del V L del y equal to 0, del u V del x plus del V V del y equal to 0. Similarly, for the Navier-Stokes equation, you will still have u du dx plus v du dy equal to minus 1 over rho dp dx plus g rho L minus rho v plus, okay, dp dx is your, again comes from your Darcy. When you go to the two phase, you will have two such equations, one for the solid phase, one for the liquid phase, one for the gaseous phase. Okay. So, this is important to know, and once when you look at the, for the brevity of time I cannot cover that, I had it all in my notes, but I just want to finish off for the last 5 minutes with a little bit of boiling. Okay. Any questions on this? At least I know this is very high level as to what happens, but I am just trying to give you a physical picture of how the flow looks like in a porous medium, and what are the different, like gravity and capillary forces, the interplay of these two is very important. And just to, this is my second key message. My third key message is, depending on in what regime, in what domain, whether it is a liquid film or the two phase or just the gaseous phase, where you are doing the analysis, you need to consider the constitutive phases and depending on that your number of governing equations maybe for just one phase or maybe for two phases. Okay. All right. I think with this background, if you now go through the book chapter, you will understand more. At least the physics part is, I would think, is okay. All right. Let me discuss a little bit on boiling now. Boiling on horizontal surfaces is what I will discuss. Boiling on vertical surface, by the way, a lot of the equations analysis again for they are very similar. Of course, the physical phenomenon is different. In one case, vapor is getting condensed to liquid, in the other case, liquid is getting evaporated to vapor. But in terms of the film, the how it comes down and all that, it's very similar in many cases. When you talk about a horizontal surface, okay, and let us consider again a horizontal surface with a packed bed of consolidated particles, which can be sand, which can be glass beads, whatever it is. Okay. So, various people did lot of experimental studies on that, and the reports have been, it is very difficult to tell some or come up with some generalized trends, because every porous medium is very different. Okay. If you think of fibrous porous medium versus a particulate porous medium, the characteristics are very different. So, therefore, it is difficult to come up with certain things to say that this is what boiling in porous media is going to look like. But that being said, let us consider what happens from our understanding. If you have a porous medium, what happens? You have continuous, you will have a flat plate, and then you will have this solid phase which is in touch with that flat plate, correct? What does that mean? Will they help you? Will they help you with better nucleation sites? Are you going to have those interfaces? If you consider a sphere sitting, you have that interface, right? And now you have a lot of them, correct? Is it good to have a lot of them very close to each other, or would you have lesser number of them sparsely placed? That is also an important, okay. That is an important question, we do not know, right. Of course, you will say that if I have more, I have more nucleation sites and there will be more bubbles formed, but then the bubbles have to escape also, correct. So, that is where the things again become complicated, and again the bond number becomes important, all right. So, when we talk about bond number for boiling, again because it is boiling in porous medium, again we have to think about permeability. Again, for the brevity of time I have to finish in 5 minutes. So, I am not getting into the mathematics here, but a higher bond number means there is higher permeability. What does permeability mean? If the vapor wants to rise, there will be less resistance in its path. Okay. So, now remember what P. K. Das was showing yesterday. Why am I considering boiling on a horizontal surface coated with a porous medium or filled with a porous medium? Well, if it happens to be that the naturally occurring substance, I cannot help, but if I want to actually have a microporous coating on a or a porous coating on a surface, my definite aim is that I want to increase the heat transfer rate, right. I may want nucleate boiling to start before. So, what Professor Das was showing yesterday, this is our boiling curve, good friend. Right. And what he was trying to show is, if we want, what is it that we want to do? We want this place to move out, this fellow to move up, a very idealized situation, right. I would start from here and maybe go there. So, am I going to achieve that using microporous substances? So, this is where what we will do is, I will now show you a plot. This is a very classic porous medium experimental study done by a gentleman called Fukusako. Okay. Sorry, for the brevity of time, I cannot, I could not go through the different. Let us see if I look at the porous. So, this is how it is. If you think about boiling in porous medium, the 4 pictures on the left. At the beginning, it is conduction, it is completely filled with the liquid, and then as you start as you start boiling or basically heating the surface, you have these modes. Okay. So, now let us focus on here, right. So, the first what Fukusaku found was, he was doing it in the packed bed of glass beads I believe, yeah. This is glass beads and he used Freon 11, refrigerant 11. Okay. What did he find? So, he did it variety of experiments. The first one was just a flat plate, and then he had glass beads of different diameters, starting from 1, 1.1 rather, to 5.3, 16.3. Clear? What did he find? The first one, which is these circles, I am sorry this is a crowded curve, but has a lot of information. You see, this is my classical boiling curve. Of course, he did not do this part because this was a heater controlled experiment. So, he could not get this transition boiling curve. When he did that with the different ones, at the larger bead diameters, what do we have? We have something very, very close, because this is high bond number. Okay. And then as he kept decreasing the sizes of the glass beads, he found two things. One is the desirable stuff, of course, this is moving towards the left, and slowly, you know, this phenomenon of this peak followed by the trough is slowly becoming shallower, right. If you think of this really low bond number ones, he was able to go like this. Clear? Now, but at the same time, the critical heat flux is not going up, the maximum critical heat flux is still over here. This was for glass beads. Okay. But later on, there were quite a few other people, other researchers who tried other sorts of microporous surfaces, etc., and were able to show that the heat flux also, critical heat flux, can also go up. Now, what is the reason here? The problem, I won't say a problem. So, one of the features of using glass beads, and let us consider to be for the sake of simplicity, these are spherical beads. Okay. What does it mean? If you want to increase the bond number, you need to have the larger beads, right, lesser number of nucleation sites. You want to increase the number of nucleation sites, the bond number also goes down. So, in other words, the pore size and the porosity are interrelated, correct. So, if I want to increase the pore size, I have to increase the bond number. I have to reduce the number of nucleation sites, correct. So, that was what was happening here. If one thing was improving, the other thing was going down. So, that brings us to the case that now, can you come up with other materials where you can achieve both? You have high permeability, but at the same time you also have larger number of nucleation sites. Okay. So, that is where people have tried different things. Okay. What Professor Banerjee was talking about yesterday is the other extreme. You have these nano structures, okay, nano pillars on the surface. Okay. So, that is one end of the extreme, but of course, these are not very easy to implement. Okay. But implementable solutions, the patterned surfaces, roughened surfaces, these have worked before. All right. So, now what I will end with is with a few words about a material that we have been working on in our lab, and which is what is called a metal foam. A metal foam looks like this. A metal foam is a high porosity medium. We are talking about porosities of 90% or higher, at least 85% or higher. Okay. So, most of it is void, right. But the characteristic feature of the porous medium of this metal foam is you can keep the porosity constant and vary the pore size, and you see over here the three figures right down here. These are larger pores, medium pores, very small pores, and what we call in porous in metal foam literature is this is different PPI standing for pores per inch. Okay. All these correspond to the same porosity, maybe 90%. So, you understand? So, I am able to have largely, I am able to reduce or have reasonably high permeability, and at the same time increase nucleation sites as I go from lower PPI to higher PPI. Possible? True? Now, what is the most optimal configuration? We really do not know, but some of the experiments that have been done before, they suggest that this does help in increasing the critical heat flux as well compared to a flat surface. Okay. How will the boiling curve exactly look like? Some people have reported that, but there is definitely, it is a function of the materials, the fluid, etc., etc. So, Kaushik, who is my student, this is his PhD thesis, a part of his PhD thesis. So, hopefully, how does the boiling curve look like as a function of porosity and pore size? Maybe 2 years down the road we will have a better answer. Okay. Can you think of a gradual increase or a layered metal foam where you have lower pore size close to the surface, and as you go up you have larger pores, so that once the bubble is nucleated, as it moves up there is not much of a flow resistance and it can move to the free surface? Yeah, possible. Not an easy thing to manufacture, because these uniform pores are, they are reasonably well mass manufactured. Okay. So, these are some of the things that we are looking at. So, the last thing I want to point out is about hysteresis. Hysteresis curve we know, right, when you heat it up you get one curve, and when you cool it down, if it is a temperature controlled experiment, that is the hysteresis, right. But porous medium can help in remove or at least minimizing, if not eliminate, the hysteresis. We saw some of that, especially for the low bond number cases. You see there is no hysteresis, it is just going up like that, and probably if you cool it down it will come down like that. Unfortunately, not many people do the cooling down experiments, but that is also something we want to do and try to see if hysteresis exists for metal foams. All right. So, and the last example that we are talking about, that we can think of, is direct contact condensation using a porous medium. So, porous packings in direct contact condensers have been used in the past, not a whole lot, but limited number of studies, and so we are also looking at using structured packings as well as metal foams to see if we can come up with more compact direct contact condensers. Okay. This is where the vapor comes from the bottom, the liquid is sprayed from the top. Clear? All right. Thank you very much. I know that was a little wayward, too many topics covered in half an hour, but I just wanted to give you a flavor of the different things under boiling and condensation in porous medium, and hopefully you will be able to take it forward if there is interest. Okay. So, thank you very much. If you have any questions, you can ask me maybe after the exam, after the valedictory function. Okay. We need to get on with the exam right now. Thank you very much.